All right, so for chapter 4 and 5, what we're going to be talking about is this new idea of forces. So we're going to mostly focus on chapter 4. There's one section of chapter 5 that we'll cover. We're going to skip the rest, and I'll kind of point that out to you as we do it, but I'm going to kind of jump around and kind of just talk about all the stuff at once since they both chapters deal with this kind of same idea. So we can talk a little bit about forces, what they are conceptually. So far, what we've talked about up through these first 3 chapters is this idea of motion, right? That we have these objects we've talked a little bit about with our kinematics and our projectile motion going in 1 and 2 dimensions. We've talked all about how these objects move around, but with these forces, we're going to be kind of talking about why they are moving in the first place, right? So conceptually, you can just kind of think of forces simply as some sort of push or pull, right? If you push on something, right, or if something pushes on you, or if something pulls you, or something like that, there are forces that are being exerted between the two of you, right? Between you and whatever object you are grabbing, right? And so what we're going to see is that with these forces, we don't necessarily need them to maintain our motion. What we need is these forces to change our motion in some way. What we're going to see is that forces cause acceleration, right? They cause masses to accelerate. So the first thing that we'll want to go over conceptually with this kind of stuff is Newton's 3 laws of motion. So we have these Newton's laws of motion. So we want to go over all 3 of these. There's one in particular. The second law is what we're going to be mainly using to solve problems with, but it's going to be very important to keep in mind the first and the third laws as well, right? So make sure you understand what is going on with all 3 of these. So the first law we have is we can state it something like this: objects remain at constant velocity until a net force acts on them. So objects remain at constant velocity until a net force acts on them. So what do we mean by net force? You can have multiple forces acting on something. What we're going to see is, though, that force is a vector, so you can have 2 different forces acting on something and have them cancel out so that this object essentially experiences no net force, right? No total force, right? If you have something pushing to the left and you have something pushing to the right, you may still just remain sitting there, right? If these forces cancel each other out. So these objects are going to remain at a constant velocity, which means they could be at rest or in motion, just as long as the velocity is constant, right? 0 is a constant velocity. So constant velocity, right? Same speed and same direction until some sort of net force acts on them. You may have also heard this phrased as: an object in motion stays in motion until a force acts on it, and an object at rest stays at rest until a force acts on it. This is kind of just a little bit more of a stricter way to do it. We're saying that until you have some sort of force, net force acting on an object, that object will just remain at whatever constant velocity it is currently at. So this leads us into then Newton's second law. So it's a very short mathematical equation that we can write, but there's a whole lot of information packed into this. So we're going to see is that the net force, right? So I'm writing this, our forces are vectors, so you do need to keep track of the direction that they are pointing. The net force acting on some object is equal to that object's mass times that object's acceleration. So what I mean by there's a lot of information packed into this, so let's really go over all of this. So we have the net force. So if I add up all of my individual forces acting on some sort of object, I can set that equal to that object's mass times its acceleration. So of course, this is where we can see the connection to the first law here, right? We have, if there's no net force, if the net force is 0, right, then our acceleration also has to be 0. So this is a vector equation, right? We have our forces. So if we have 2-dimensional forces, again, we can just break this equation up into both x and y directions, as we should be familiar with by now, looking at our projectile motion and our relative velocities, right? So it is a vector. We are going to be working with it in 2 dimensions, so all of those mathematical rules will still apply. So this net force, again, we are adding up all of the individual forces on some object. We could have a whole bunch of different forces acting on one object, and this net force here that I'm writing, right, this is kind of the sum of all of these forces, right? So you could have gravity acting on something, you could have friction slowing something down, you could have some sort of normal force, you could have some sort of tension, all these other kinds of things. I'll go into more details about all these different types of forces that we're going to have. But you could have, say 6 different forces acting on one object, and then you'd have 2 equations with, 6 terms over here, right? Both of them, they could all have an x and a y component. They could all add up, and you have to set them equal to this mass times acceleration. So this is Newton's second law. It's one of the most important ones. This is the one that we're going to apply the most directly when we're problem solving, right? Add up the forces, see how the object moves, or look at how an object is moving and see what you can learn about what forces are acting on it. Along with this, let's take this time to look at what are the units of these forces, right? So we have some sort of force. So the units of force in this case are going to be mass times acceleration, which gives us kilogram meters per second squared. Or we can say this is equal to, this is what the actual standard units are, right? Of kilograms meters per second squared. Or we can say the shorthand for this is they are 1 Newton, right? So this is 1 kilogram meter per second squared is equal to 1 Newton worth of force, but the Newton is just another name for a kilogram meter per second squared, right? Okay, so we have this Newton's second law. We also have Newton's third law. Okay, so in this one, what we're going to say is for every force, there is an equal in magnitude and opposite in direction reaction force, right? So I know my handwriting is getting a little bit sloppy there, but yes, we have for every force, there is an equal in magnitude and opposite in direction reaction force. So again, you may have heard this one just as phrased as like there are equal and opposite forces. I want to specify again, it's equal in magnitude and it's opposite in direction. So these forces always kind of come in pairs when you're talking about 2 objects that are interacting with one another. So it's very simple, right? If you go up to a wall and you lean on the wall, you apply force to the wall, right? You push the wall, say, to the right. The wall then pushes you to the left, and it's going to be pushing back with exactly the same strength of force. And this is true for every single possible pair of forces you can ever imagine, right? Anytime you apply a force on something, that object is also necessarily applying a force on you. So even when we look at the force due to gravity, let's take a look at this conceptual example for a second. We can kind of do some thought experiments with this and kind of see how these laws play out. So let's see what the force of gravity must be. So we can say the force of gravity on some object is going to be that object's mass times the acceleration due to gravity, right? So we know, right, our forces are equal to mass times acceleration. Our net force is equal to mass times acceleration. If gravity is the only force acting on us, the force that we experience is this. It's m times g, where m is our mass, g is our 9.8 meters per second squared that we're used to, right? So let's see. So again, this is the force that the Earth is exerting on me. I am actually also exerting this same magnitude of the force on the Earth, right? So this might seem a little bit awkward at first. The Earth is pulling on me just as hard as I am pulling on the Earth, but of course, this doesn't necessarily mean that, if I jump up in the air, right? Make sure you understand the difference between force and versus acceleration is what we're talking about here. If I jump up in the air, the Earth is going to pull me back down with a magnitude mg, but I am going to pull the Earth up with a magnitude of mg, right? But of course, my acceleration is going to be this. It's going to be 9.8 meters per second squared. The Earth's acceleration is going to be much, much less, though, right? And again, it's because the Earth has a much larger mass than I do, right? So my mass times my acceleration due to gravity, this same magnitude of force will be the same magnitude of the gravitational force that I pull on the Earth with. But again, we can look at Newton's second law, right? If the overall strength of the force is the same between me and the Earth, right? My mass, right, is much smaller, so my acceleration will be much larger. The Earth's mass is much larger, by a few billion times, and so the Earth's acceleration will be much smaller. So it's the same force being exerted on me that is being exerted on the Earth, but the Earth has much more mass, so the Earth does not accelerate as much. And so yeah, so this is kind of an important thing to understand, right? The more mass something has, if you push on two different objects, you push on them with the same force, right? If you push a cardboard box across the room, um, maybe you can accelerate it up pretty quickly. Whereas if you try to push a couch across a room or something like that, you apply the same force on it, right? You push on that couch just as hard as you push on the box. But of course, the couch has more mass, and so the acceleration will be less if you apply that same force. So again, this should also make sense. If you have a larger object with more mass and you want to accelerate it at the same rate as something smaller, you have to apply two different forces to them, right? You have to push harder on the heavier object. And again, this also kind of works out with gravity, right? We have said that everything falls at the same rate regardless of the mass, and this is true. However, again, you can see the Earth is going to be pulling on these heavier objects harder, right? So they have more mass, so the force on them is greater, but the acceleration will be the same, right? Okay, so these are our three laws that we're going to be dealing with that we have to keep in mind for all these different situations and all these different problems that we're going to have to solve. Object at rest remains at rest, object in motion stays in motion, or object remains at constant velocity until a net force acts on them. We have the net force is equal to mass times acceleration. Then we also have, for every force, there's an equal in magnitude and opposite in direction reaction force, right? Again, when these objects interact with one another, you can't ever just apply a force on one thing and not have there be a force applied on something else, right? Is what we're saying with this third one. If you're pushing something around, it is also pushing on you, but it just kind of depends upon the difference in masses as far as how those objects then react to those forces, right? How they will accelerate because of that. All right, let's talk about another tool that's going to be very useful for us when we are solving these types of problems that we have and we're setting up these situations. So you have another tool called free body diagrams. These are just very useful to help us visualize exactly what is going on with all these forces. So whenever you have a problem and you're working with several different forces acting on one object, it's very helpful to essentially graph the forces, which is kind of what this is. You can just draw a simple object and then actually draw out what the different forces acting on that object are. So let's say we'll have a simple free body diagram of me standing here on the ground. You don't have to go into any detail with these if you don't want to, but if we have me standing here, what are all of the forces acting on me, right? So that's what you want to first ask yourself. Well, of course, gravity is pulling me down, right? It's going to be so great. The direction of gravity, it's always going to be pointing straight down towards the center of the Earth. That's the direction that gravity will be pulling me. But of course, am I actually falling down through the center of the Earth? No, if I'm standing here on the floor or something like that, there is another force, right? There's some force from the floor. What do we want to call that one? So first of all, what direction is the floor going to be is the force from the floor going to be acting on? It's just going to be going straight up. And what am I going to call it? In this case, I'm going to call it a normal force. So these are going to be two of the different types of forces that we'll talk about, and kind of two of the most common ones that we run into. So gravity, obviously, the force of gravity from the Earth pulling us down towards the center of the Earth with a strength of m times g, right? And then there's also a normal force from the floor itself. So what do you mean by this normal force? Why is it called normal? A normal force is essentially just a contact force. So anytime you have two surfaces kind of in contact with one another, there is some force in between them. In this case, the normal force tells us normal is kind of, in mathematical terms, it's another word for perpendicular. So whenever you have these surfaces in contact with one another, in case my feet on the floor, the normal force is going to act in a direction perpendicular to that surface. So if the floor is flat, the normal force will be straight up. So of course, if I stand on an angled surface, the normal force would actually be kind of up off at an angle. And I'll show you some examples exactly of how all of that stuff works here in a little bit. So yeah, so this would be my free body diagram for this situation. Gravity pulling me down and this normal force from the floor pushing me up, right? So again, it's also important to understand this normal force is just going to do, right, as much work as it needs to basically not have me break through the floor and fall through it, right? Whenever you set something like on a shelf or anything sitting on the floor or anything like that, there's always this normal force that you have that is acting on that object, right? It's just this contact force between any two surfaces, right? So I have this notebook here sitting on this table, right? it's not falling through the table, and it's doing that because the table is applying a normal force up on this thing, right? So anytime you have these two surfaces in contact with one another, you will have this normal force acting perpendicular to the surfaces themselves, right? So it's just a very simple example um, of a free body diagram. So another simple example that we can do would be, let's say I go skiing, which I'm not very good at, but for the sake of this problem, we're going to say I am now going skiing. So we're going to also assume that this is my skis are very some sort of angle here. So that my skis are very slick, and that in this case there is no frictional force. So we'll talk about friction here in a second. We'll get into all of our different types of forces. I just want to show you some of these free body diagrams here for a second. We have a very similar situation as what we had before. Right, so in this case, I'm standing still on the floor. We have our two forces. They cancel out, and I don't go anywhere. In this case, though, if I'm standing on this slope, right, on the ski slope, and there is no friction on it, which direction is gravity going to pull me? Still going to be pulling me straight down. Which direction is the normal force going to be acting? The normal force in this case, since I'm on this angled slope, is going to be going up off at this angle, right? It's going to be perpendicular to the surface that I'm standing on. So of course you can look and just visually see, right, if I add these two vectors together, which direction am I going to go? My overall vector, I'm not going to draw it on here, right? I just want to draw the individual forces, not what the net force is. My overall individual forces, though, when I add them together, will work towards pushing me, will accelerate me down this hill, right? Which is exactly what you'd expect if you have a person on skis there. So these are just some kind of simple examples of free body diagrams. But before we move on, before we do any more examples, let's talk about the different types of forces that we are going to encounter while we work these problems. Okay, so we have, make sure I'm actually on screen here. We have types of forces. So obviously we have gravity, right? And for gravity, we have a nice formula that we can write, which is always just going to be m times g, right? Little g can change. When would that change? It would change if you're on a different planet, right? On Earth, it's 9.8 meters per second. If I go to the moon, meters per second squared. If I go to the moon, it's about 1.6 meters per second squared. If I go to Mars, I think I'm not sure if I'm right on this. I think it's about 3.4 meters per second squared, something like that. But it's based upon a couple different things that we'll get into a little bit later when we go into more detail about gravity, but largely just the more mass, right, the more mass of an object that you happen to be standing on, the larger its force of gravity will be and the larger acceleration you'll get, right? The moon is much smaller than the Earth. The acceleration due to gravity on the moon is about 1/6. On Mars, it's about 1/3, right? But at gravity, it's always just going to be the mass of your object times little g, the acceleration due to gravity of whatever planet you happen to be on. So yeah, so this is what we're going to have for our force of gravity. As we said, we also have the normal force. There's not really like a neat little formula for this. Usually you're just going to have to kind of see based on the context what the strength of the normal force is going to be. Again, if you have some object on a flat surface, the normal force is basically just going to be the same strength as gravity, right? But in the opposite direction. Gravity's going to be pulling something down, and if it's sitting on a flat surface, like in the case again of this notebook here sitting on the table, gravity's pushing it down. The normal force is pushing, the normal force from the table is pushing that book back up. And the strength has to be, in that case, the same as the strength of gravity, right? You can just look at the book and you can see that. Okay, so we have the normal force. We also have something called a tension force. So how is tension force going to work? Again, this one we don't have a nice, neat little formula for, but we can think about it like this. Tension comes when we have objects connected by strings. So let's say I have a block, and then I have it connected to a string with another block, and I pull on either side, right? So I'm like pulling these objects apart. There's now tension in the string, right? So the way tension works, the way we have to think of it is like this. The tension, the magnitude of tension throughout the string, so the strength of tension, the magnitude of tension throughout the string will remain the same. Throughout the string is the same. So if there's this string here, this end of this string tied to this block, it's going to apply a force to pull this block to the left. This end of the string is going to pull this block to the right, and the strength of this, the direction is different, but the strength of this tension force has to be the exact same. I don't know what that force is, again, depending on how hard they're being pulled to away from each other. The harder they're being pulled this way, the more taut the string will be, the stronger that tension force will be, right? So the direction changes, but the strength of this tension force has to remain the same throughout the length of the string. And really, what you can think of this is very simply a bunch of Newton's third law, right, over and over again. So each point on this string here we have all is just made of a bunch of little molecules, and all those molecules are pushing and pulling on each other with the exact same strength, right? It's Newton's third law over and over again. You have an equal and opposite force here, equal and opposite force here, equal and opposite force here, all the way down the length of this string. All these little particles that make up the string are, pulling on each other back and forth as you pull these two blocks apart from one another. And so the way it works out is the strength of the tension is the same. The direction will be, again, just in the direction of the string, but can change, right? Obviously, in this case, if I'm pulling this block to the right, the string is trying to pull it back to the left, and vice versa for this one. So again, the magnitude of the tension throughout the string is going to be the same. The direction can change. And again, you can think of this as just you're applying Newton's third law over and over again. So this is our tension force. We also have a spring force that we will deal with. So this happens, as you would guess, when you have something attached to a spring. So let's say I have a block sitting on a table or something like that, and it is attached to some sort of spring with this wall, right? So what can I do with this block? I can push it in, right? And then what does the spring do? The spring will push back with some sort of strength. Or, right, I can push this block in, or I can pull this block out, and then obviously if I push it in, the spring pushes back against me. If I pull it out, the spring pulls back towards where it was. So it's kind of this restoring force. The spring is always trying to get this block back to just having the spring be at its rest length, right? We do have a nice neat formula for this one. The magnitude of the spring force is going to be equal to K times X. What is K? K is the spring constant. So the units of this are in newtons per meter, and then X is the displacement, right? Displacement from rest point. So right here, if I just have this spring at its rest length, the spring is applying no force on this block. If I push this spring in, if I push this block in, the spring starts to push back, but the further I push it, right, the more this X increases, the further away it gets from this equilibrium position, right? So here we have X equals 0. We can say, if we have it out here, if we have our block pushed in here, right, as this block moves to the left or moves to the right, this is our X equals 0. We have maybe X equals plus X naught, and here X equals minus X naught, whatever it happens to be. I don't know what the exact distances are. But if I push this in, the spring starts to push back, right? So X is going this direction, and the spring is pushing back in the other direction, right? And the further I push that in, the harder the spring wants to go back to where it was, right? And the opposite happens when I pull this spring. When I pull this spring, the force from the spring gets stronger and stronger, right, as I pull it away from this. And so it is this nice relationship here. K is just a measurement. It's the spring constant. It's in newtons per meter. So you can kind of think of it as a measurement of how stiff the spring is. It's pretty usual to have pretty high numbers for this because it's newtons per meter. So like even a really weak spring you could think of would still have a spring constant of a couple hundred newtons per meter. Because you can imagine, this pin here, there's that spring right inside of it. You can kind of see. Obviously, it wouldn't work from a physical standpoint, but you can imagine if I were to pull this spring out an entire meter, right, it's obviously going to lose its shape at that point. I'm just going to bend it and all this kind of stuff. But if you could pull it and have it still keep all of its spring quantities, and you could pull this spring out 1 full meter, it would be exerting several hundred newtons worth of force or something like that, something along those lines. So that's kind of what we're saying with this, right? This is a measurement of newtons per meter. The higher this number, the stiffer your spring is, right? And so again, the further you push or pull this spring, the stronger force that spring is going to exert, right? And it's always in the opposite direction of this displacement. If the displacement is negative, the spring force is positive, right? If the displacement is positive, the spring force is negative. It's always going to be in the other direction. So this is just the magnitude of it. If you want to know what the direction is, you can just look if the spring is being compressed or stretched. Um, and so then finally, the last specific force that we'll get into, this is kind of where we're dipping into some chapter 5 stuff, is the friction force. So with friction, again, when do we end up with cases of friction? So this is when we have two surfaces kind of in contact with one another, and they're either are rubbing up against one another or they're trying to. So we'll deal with this one. We'll deal with some examples of this. We'll keep talking about this one, but for now, we're going to say that the force of friction I'm going to use to be consistent with, I think this is what the book uses, what a lot of people use, lowercase f to denote friction, and it is equal to mu. This is the Greek letter mu. It looks like a U. It's the Greek letter mu times the normal force. So this times the magnitude of the normal force, right? So this is the strength of friction. Which direction is friction going to act? Friction is always going to apply a force in the direction that's parallel to the surface and opposes the motion, right? So right now, again, here's another good one we can use just this notebook for. Sitting on this table, if I slide this notebook to the left, I feel a very slight force of friction. It's not very much in this case. We feel a very slight force of friction that's trying to pull the book back to the right, right? So if I move this book to the right, friction is trying to drag it back to the left, right? And so of course, the friction is very useful, right? It opposes motion, but it's also kind of how we're able to move things around, right? When you walk on the floor, you're taking advantage of friction, right? You are trying to slide your feet backwards and then the floor pushes you forwards, right? And of course, if you have a very slick floor, then you can like practice your moonwalking or whatever. You can like walk in place, do all those kinds of fun tricks. But yeah, if you don't have friction, right, you're not going to be able to go anywhere. So this friction, we'll see in a lot of cases. It's also, again, when we're talking, we have to be a little bit careful when we're talking about wheels on the road. We'll see some examples with that. That one can be kind of tricky, right? Because it's, again, friction is going to oppose the relative motion of the two surfaces in contact. So in the case of a car tire on the road, right, the car tire is trying to pull the road backwards, but then of course, the road sits there and it's not going to go anywhere, and that's going to propel the car forwards is kind of how this is going to work, right? So yeah, so again, this strength that we talk about for this friction, we have the friction is equal to this mu. What is this mu? We know what the normal force is, right? The normal force is a measurement of how strongly you are pushing the two surfaces together, right? So the stronger the normal force, the higher force of friction you have. This mu is what's called the coefficient of friction, right? So this is just, as you'd expect, the normal force, and this is the coefficient of friction. This is simply, it's a unitless quantity, right? This is already in newtons. This frictional force has to be in newtons. This is a unitless quantity, and it's essentially a measurement of how sticky the two materials are, right? If you take a Teflon pan and you put it on another Teflon pan and you slide them around, they're going to slide around very easily, right? If you try to walk on ice, you have a very low coefficient of friction between your feet and the ice, you're more likely to slip, right? However, if you take your cleats and you go out onto a grass field, you have very good grip. You'd have a very high coefficient of friction between your shoes and the grass, right, and the ground at that point. So this coefficient of friction, the higher this number, the stronger the force of friction will be, and this is just basically material dependent, right? Different sets of materials slip or slide on each other differently, right? And it just kind of has to do with what's happening with this frictional stuff when you actually look at the molecular level, right? When you look at the molecular level, even stuff that looks smooth might be kind of rough, and so as you bring that surface up to another smooth looking but actually rough surface, you just kind of have the molecules bouncing up against one another, right? And that's kind of where this friction comes from. So the actual material itself will have a large role to play with this coefficient of friction, right? Again, if you ever tried to drive your car on the pavement, right, it works out very well. If you ever tried to drive your car, if you've had the unfortunate happening of hitting a patch of ice, right, the normal force is the same, right? Gravity's still pulling your car down and onto the road just as hard as it was before. The road's still pushing it back up. But if you go from pavement to ice, the coefficient of friction between that changes, and it gets much slicker, right? You have much less gripping force between the tires and the road. So again, friction based on two things: how hard are you pushing the surfaces together, and what are the materials made out of, right? And again, you can kind of see this one very easily, right? If I slide this notebook around, it slides around very easily. If I push down on it now I try and slide it, it gets much more difficult to try and slide this notebook around as I push down on it, right? I've increased the normal force, the coefficient of friction is staying the same, and as such, the force of friction will increase. Okay, so these will be our kind of main forces that we deal with, right? We have gravity, normal force, tension, spring force, and friction. These will not be the only ones that we deal with, but this should cover most of our cases, right? So we will have some other ones come up again, but if they do, they'll kind of be explained by whatever problem you're in, so you wouldn't want to worry about it too much. But these I'll kind of assume when when you're looking at your problems, these are the ones that you're going to want to know how they work, right? Which ones of these work. Okay. Let's then take a look at some examples of setting up these free body diagrams. Let's go back to our example with our skier. This is a really good example. This is a favorite problem of mine to ask possibly on a test. I'm not going to put any numbers to it right now, but let's go ahead and let's look at this case again. So you got this person skiing down this hill. And so in this case, for now, we're going to do the frictionless case. So we already drew the free body diagram earlier. What are my forces? I have gravity pulling me down, and I have the normal force pushing me off at this way. So let's say this is some sort of angle theta. And what I want to know is what is the acceleration of this person as they go down the hill, and what is the strength of the normal force that they see? What is the acceleration? What is the strength of the normal force? We already know what the direction of the normal force has to be. Let's go ahead and let's see how we can kind of apply our Newton's second law to this case here. So here's my free body diagram. I have my gravity. I have my normal force. In this case, we are not including friction. We'll do it again here with friction here in a second. But for now, let's just do it with this. So how do I go ahead and apply Newton's second law? So what does Newton's second law say? As a refresher, our F net is equal to ma. So you do want to go ahead and break this down into both x and y equations and see what you can learn. Okay, so in this case, what do we want to do with our coordinate system? When we have something that is actually moving down a hill like this or moving down some sort of incline, you don't have to do this, but I think it makes things a little bit easier. I'm actually going to tilt my coordinate system as well. So I'm going to say that the positive y direction is at an angle such that the positive y direction is exactly perpendicular to the surface, pointing in the same direction as the normal force, right? And then I'm also going to say that my positive x direction in this case is going to be down the hill. So I'm going to tilt my coordinate system itself. Again, you don't have to do that. Your coordinate system is always your own choice. But for these types of problems, I think where you have something actually moving down the hill, or actually moving down some sort of incline or up some sort of incline, I think this is very helpful. And the reason is because it ensures that your net force is now entirely in the x direction, right? Obviously, you still have some y components from the normal force and from the gravity. But let's go ahead and let's split these up and let's see what we get for this. So let's add up all of our forces, right? Our net force in the x direction, and let's see what we get. So in this case, if I add up all of these forces in the x direction, what do I have? So I have my two forces. My normal force is entirely in the y direction, so I don't have to worry about that. My gravity force, though, in this case, my gravity is straight down, but because I tilted my coordinate system, the force of gravity is actually in both the x and y directions. So which direction is it exactly? Well, we know this angle here, the angle of my slope is theta. This angle here is actually also going to be theta, right? So we have the angle between the horizontal and the slope itself. This angle is theta. This angle here between my new y-axis and gravity, You can kind of imagine this. You can go through, you can do the geometry yourself, or you can just take my word for it in this case. You can kind of visualize it, right? If you make this hill really shallow, and you basically make it not steep at all, then gravity is coming straight down, and the y-axis would bend back towards gravity. Um, so as we make this hill steeper, right, the new y-axis gets moves away from gravity in the exact same way that this moves away from the horizontal axis. So yeah, this angle theta is also this angle theta here. So the our gravity vector has the angle theta between itself and the y-axis. So in the x direction then, this is my x component of gravity, right? The part of gravity, here's my y component of gravity, here's my x component of gravity. My x component of gravity is actually opposite this angle, and so what I end up with is when I add my forces up in the x direction, I get mg times sine of theta. And what is this going to be equal to? In this case, I know that my net force is all in the x direction, so this is going to be equal to m times a. Let's go ahead, let's do this. Add up all my forces in the y direction. In the positive y direction, I have the normal force, and in the negative y direction, I have mg cosine of theta, right? And then what is my acceleration in the y direction? Am I jumping off this hill? Am I sinking down into the snow? As far as we know, no, that's not happening. I'm just sliding straight down the hill. So my net force is all in the x direction. So my net force in the y direction, my acceleration in the y direction is 0. So it would still be m times, as you say, m times ax, right? And I can do m times ay, but we know that ay is 0. So right away, we can actually answer both of these questions very quickly, right? Um, my net force is all in the x direction in this case, and it's going to be mg sine theta, which is equal to m times a. So we can say cancel out the m's, and we have g sine theta equals a. So our acceleration as we go down this hill is equal to g times the sine of theta. So remember, let's think about, does this make sense? What if our theta is 0, right? So if I have my angle be 0, I'm now not on a hill. Sine of 0, if we remember, if we do our, think about our unit circle, think about our trig, sine of 0 is 0. And so if I'm sitting on a flat surface, my acceleration is 0. So that should make sense. However, and then as it gets steeper, right, sine of theta increases. As it gets really steep, what if we had this be a cliff, right? Let's say I'm just sliding down the side of a 90-degree angle straight down cliff. Now my angle is 90. Sine of 90 is 1. My acceleration is g, right, which should make sense. I'm just in free fall at that point, right? I've just skied off the edge of a cliff, and I'm just falling straight down. So yeah, so this should make sense. This should be a fairly intuitive result. Maybe the steps to get there are kind of new, and that's okay. We'll do plenty more of these examples. We're going to use this kind of analysis a lot throughout the rest of the semester. But the actual result should kind of conceptually make sense, right? This acceleration is based upon whatever planet you're on, right? The strength of gravity is going to affect how fast you slide down the hill, but also essentially how steep the hill is, right? So we've got that. We figured out what our acceleration was, the strength of normal force. Well, we know in the y direction, Fn minus mg cosine theta has to be equal to 0. Simply rearrange it, and we can say the strength of normal force in this case is just mg cos theta, right? You can add this to both sides and bring that over there. So this is going to kind of be the process that we go through over and over when we are doing these types of problems. Draw your free body diagram, look at your forces, break them up into the x and y, and then write your Newton's second law equations where you have F net equals ma, and make sure to do it for both the x and y direction. So we're going to leave it at that for now. I'll have plenty more examples of where we go over this stuff though later on. So we'll see this. We're going to do this. We're going to get very good at this stuff. We'll practice it a lot.